Okay, we will start from this parity violation in beta decay processes. What is this parity? Parity means nothing but a mathematical concept which just flip the coordinate axis. So, for example, if you are having a right-handed system, which means that if you consider like these x, y, z coordinates in positive quadrant, okay, and if you use some parity operation, then that axis will be flipped. This is flipped. So that means that your x, y, z will become now your minus x, minus y, and minus z. So your this is not there. So this will be your minus y. This will be your minus x. This is your minus z. So this is just like a mirror image of this one. So this is your parity operation. If you do the parity operation, then your x will become minus x, z will become minus z, and y will become minus y. Okay, so that is what the parity operation. It is a mathematical concept, and we'll be having, if you are considering the coordinate that is the Cartesian coordinate x y z, then that will be flipped into minus x minus y minus z, uh, like that. Okay, so that is the parity operation, and you have different kinds of that. We will see that. So if you consider any physical quantity like momentum, force, or any other kind of physical quantities, so these parity change affect these physical quantities. But remember, physical laws are invariant under any parity operation. So if you consider the case, for example, position vector is a physical quantity. So that will be changed from R to minus R under parity operation. So it will be, if you do a parity operation on R, it will change to minus R. If you do parity operation on momentum, that will change to minus P, because momentum is, if you consider that operator, and it is dependent on tau by tau x and all those things. So it will change to minus P. And if you consider acceleration also, it is also dependent on those coordinate systems. So that will change to minus A. If you consider force, that will change. It is, of course, it is dependent on this acceleration. This is MA. M is constant, so that will result in minus F. Okay. So these physical quantities, or any other physical quantity also, many other physical quantities are there which will change under parity operation. Okay. So and there are some operations or physical quantities which will not change the physical their uh, that that will not change under parity operations. For example, if you consider f equal to ma in your real world, okay, then in mirror world, that means that after parity operation, then you will get your f which is same as your f is going to be minus f, okay, and your a will become minus, so it will become minus ma. So effectively, this is nothing but f equal to ma. So which means that even if you consider the real world physical equation or physical law, or the mirror world, or the after parity operation, this the law holds. Okay, okay, this is the Newton's law that holds in any parity operation. So if you take any other physical laws, the law will be the same. Law will not vary, but physical quantities will change, as mentioned here, and the law remains the same. So laws will not, physical laws are invariant under any parity change or um, coordinate transformation or like that. So they are invariant under parity operation. Physical laws are invariant under parity operation. So whatever Newton's law that we do in real world will be applicable in the mirror world also after parity operation. Okay, there are some quantities which are not obeying or which will not change under parity operation. For example, if you consider the angular momentum, if you consider angular momentum, that will give you L equal to minus R cross minus P in mirror world. Okay, so which means that your R will change to minus R and P will change to minus P. And if you take L, which is R cross P in real world, and that will be in mirror world, it will be L will become minus R cross minus P. That will give you same result. Okay, so angular momentum is invariant under parity operation. Okay, so there are some physical quantity which are invariant under parity operation also. So angular momentum is one of them, one example of such physical quantities. Okay, now if you consider the um, different interactions or forces in nature, and there are four different types of interaction or different um, what is that forces that is existing in the world. They are that the gravitational force, the strong nuclear force, weak force, uh, all those things. Okay, so the in electromagnetic force, all those forces, when you consider among them, only these weak interactions are not following this parity symmetry, which means that they violates the parity symmetry, uh, and all other forces will follow the parity symmetry, which means that they will not change in the real and mirror world. Okay, so only weak interaction has the parity symmetry violation. And also we have one another example I have given here, nuclear spin, for the quantity, physical quantity, which does not follow or which does not change under um, parity transformation. So nuclear spin will not change, and angular momentum also will not change under parity operation. Okay, and we also said that the weak interaction among the different types of interactions, different types of force existing in the nature, the weak interaction or weak force is the force which violates the parity symmetry. Okay, so there will be different in uh, in the real and mirror world. They cannot be equal. Now, if you consider the case of different particles, first we have to consider the handedness of particle, what is called as handedness. We define one term, which is the handedness of the particle when we go for the parity operations. Handedness, okay, handedness. So handedness of the particle can be defined like this. So if you consider the nuclear spin or the spin of the particle in one direction, and the associated, for example, the large arrow or the bigger arrow, which is having big head size, which is representing the nuclear spin, and the small arrow with a small head, this one is representing your the momentum. Okay, momentum, that is direction of motion, momentum corresponding to that direction of motion. So your nuclear spin and the direction of motion, that is momentum direction, also both, if both of them are in the same direction, such particles are called as right-handed particle. And if the condition is like, if the direction or the momentum of the particle is in the opposite direction of that of the spin direction or the nuclear spin, and then such particles are called as left-handed particles. So these are left-handed particles, these are right-hand particles. So once again, I will repeat this. So if you are having the particle which is moving or which is having momentum direction, okay, that momentum direction which is opposite to that of the spin direction, which is called as left-handed. Okay, that is this one if it is opposite. And if they are having same direction, that is the momentum or the direction of the motion of that particle and the spin, which are in the same direction, then it is called as right-handed particles. Okay, that is the handedness of particle. And from by using this handedness of particle, we define the parity for the interaction, for example, in the case of beta particle decay. So that we will discuss now. So when we analyze the neutrinos are also class of particles. There are electron neutrino, muon neutrino, tone neutrino that we will discuss in the particle physics side. So these neutrinos are also particles which have this kind of handedness. So this neutrino or the antineutrino, when we observe these particles, neutrinos and antineutrinos, we didn't observe any single neutrino experimentally. There is no single neutrino with right-handed, as right-handed particle. Okay. Similarly, there is no antineutrino which are left-handed. Okay, so if you consider neutrino, they will always in left-handed. They are always left-handed. If you consider anti-neutrino, they will always right-handed, which means that the spin of that neutrino and the direction of their momentum or the direction of motion will be always opposite for the case of neutrino. If you consider anti-neutrino, the spin and the direction of motion, that momentum will be having same direction. That spin and momentum direction will be same, and that is for the case of antineutrino. No neutrino will ever have a spin direction which is same as that of the momentum direction or the direction of the particle. So there is no such cases observed, which means that nu with RH, that is right-handed, nu as right-handed particle, is never observed. Similarly, antineutrino with as an left-handed particle never observed in nature. Okay, this is a peculiar nature of the neutrinos and antineutrinos. They never observe in these two formats. Okay, if they are moving, they move while they move. For example, neutrino, if they are moving, they move in such a way that their spin will be opposite to their momentum direction. And if you consider antineutrino, they will move when they will move, their spin always try to be in their direction of motion. Okay, so that is the case. So we never observe any neutrino with the right-handed form. We never observed any antineutrino with as a left-handed particle. Okay. So for in the case of, if you consider for photons also, there is a left-handed and right-handed particle. But if you consider right circularly polarized, they are right-handed particles for photons. If you consider left circularly polarized case, then they are left-handed particles when you consider photons. So photons are also in this category, right-handed and left-handed particles. So when photon become right-handed, they are right circularly polarized, and when they are left circularly polarized, they are called as left-handed photons. Okay, so that is just mentioning some other cases for other particles also that we can use these left-handedness and right-handedness. Okay, so when we consider two different particles, no, in normal case, if you consider the parity operation now, if you have a particle and which is left-handed, in this case it is left-handed. This is left-handed particles. So in left-handed, we know that the spin will be opposite to the momentum direction or the particle velocity, that motion direction. So this is left-handed. Similarly, this in this case this is right-handed, which means that the spin direction is same as that of the motion direction of motion. Okay, so the bigger arrow which is spin and the small arrow head which is the direction of motion or velocity. So when they are in the same direction, they are right-handed. So when we take the parity operation of these particular particles, when you take the parity operation, let's say this is the parity operation, like a mirror. Okay, so you can have this kind of possibility. Okay, so let's now do not consider this as neutrino and antineutrino. Let's say this is not the case. Okay, for now. So in this case, we have right-handed particle. Here we have left-handed particle. When you take the parity operation, they will become right-handed particle. Okay. So when with left-handed particle under parity operation, they will become right-handed particle, and the spin and this momentum direction will be in the same direction. Okay. So the under parity operation, I already told you, under parity operation, spin do not change. Spin do not change under parity operation. So this arrowhead, bigger arrowhead will not change under this parity operation. So this is pointing in this direction. So it will point in the same direction when you consider that. Okay. So spin will not change. In here, spin is pointing this direction. Okay. So here also spin is pointing this direction. But the momentum will change. Okay, momentum direction will change because momentum will become minus p under parity operation. So that will change, that direction will change. That what we can see in this case. We have a momentum which is in opposite direction as compared to this case. So this is in this direction. So this is left-handed particle, and that is converted into a right-handed particle under parity operation. Similarly, if you consider the second case, right-handed particle, which is converted into a left-handed particle in this case, we can see that spin will not change, spin direction is same, but the momentum will change, and momentum direction is going to change. That will give you a left-handed particle. So a right-handed particle is converted into left-handed particle. A left-handed particle is converted into right-handed particle by the action of parity operation. Now, if you consider the neutrino here, okay, so neutrino we can say that anti-neutrinos are right-handed particles. Okay, anti-neutrinos are right-handed particles. So we can say this is. Sorry, I should not like this. So let's say this. We know that these are anti. So this is, okay, this is the okay, this is let's say this is the right, this is the right-handed, so this will be the anti-neutrino. Okay, and this is left-handed, this will be the neutrino. So if you take the parity operation in this case, what we can say that this anti-neutrino will become neutrino here because this is left-handed. Okay, this is left-handed system, so it should be a neutrino, and this should be an anti-neutrino because it is right-handed. Okay, but when you consider this case, the anti-neutrino, this is anti-neutrino, this will become a neutrino when it comes to this side, but that is not the case in the normal particle. For example, if you take photons, if you take left-handed photons and take a parity operation, do a parity operation, and that will become right-handed right-handed photon. Okay, if you take any other particle also, the same particles with their handedness will change. But in this case, the new bar, if you take this anti-neutrino, it will not change into left-handed anti-neutrino because left-handed anti-neutrino will not exist. So they are not formed. So this is a kind of violation in the case of parity operation, in normal parity operation. So when it comes to the neutrino anti-neutrino case, We never observe a neutrino which is RH, which is right-handed, and we never observe an antineutrino with left-handed. So the scenario on this left-hand side, this side, which this will never occur. Okay, so let's say this is a neutrino with right-handed, and if this is a new antineutrino with left-handed, this is not possible. Okay, in normal cases, normal particle, the particle can be in right-handed or left-handed under parity operation. So if you have a left-handed particle, do parity operation, you will get right-handed particle of the same type. And if you are having a right-handed particle, you do parity operation, you will get left-handed particle. So the particle will not change, but their handedness will change. Like the motion and spin will change, direction will change. But we in this case it is not possible. So because when you take neutrino, you do parity operation, you get a right-handed neutrino. That is not possible because right-handed neutrino will not exist. We didn't observe anything like that. So this is a kind of violation of parity. This is a kind of violation to parity when the case of case of neutrino and antineutrino, when we consider the case of neutrino and neutrino. Now we will go to what is the importance of this in beta decay process, why we have to study that. So when we consider the beta decay, which is also associated with the neutrino antineutrino emission, okay, it is a weak interaction. Beta decay process is a weak interaction. So when we consider that beta decay process, like for example, in this case, this is performed by Wu and his co-researchers, and this is called as Wu experiment. If you cannot see that, this is called as Wu experiment, WU. And what they have done, they have used the cobalt to nickel transition or the decay process that we already discussed, I think. So when we have the cobalt to nickel transition or decay, we have an electron negative, that is negative charge, electron which is coming out, that is negative beta decay now. This is negative beta decay. And we have an antineutrino which is coming out along with this reaction. So we have the cobalt which is 60, cobalt 60, which is decaying. I think my question. So this cobalt which is decaying into nickel. So I can draw like, okay. So this cobalt is decaying into nickel. Okay, nickel will end up in the excited state, and it is also having 60 atomic mass, and this is 27. Here it will be Z plus 1, I think. Okay, so 28. Okay, so that is the reaction. So in this negative beta decay, they have done this experiment that is called as Wu experiment, and we have the in this particular case we have the negative beta decay, the neutron which is going to to decaying into a proton and an electron plus an antineutrino, and this electron and antineutrinos are coming out, and the proton will be inside the nucleus, and all those things we have already discussed. And what is neutron in quark model, that we will discuss later also. That is UDD, that will become UUD when you consider the quark model. That will become E minus plus neutrino and all those things. So this is not that much important. We will discuss about this in when you do the particle physics. So actually one D quark which is converting to a U quark, you can see from here, this D is converted into this U, and plus this electron plus this antineutrino. So that is what is coming. Okay, actually it will come from a D UDD to UUD, and that will be transferred into a W bosons, something like that, to become some intermediate particles are there, and that will again disintegrate into this U and the electron and the neutrino, antineutrino. So that will discuss, and you can refer in any other books also. So the actual process happens in the quarks model. Okay, so that will be happening like this. So initially they will be transferred into some intermediate particle, then again disintegrate into electron and neutrino and the U. So that's what is happening here. That is basic process in the electron beta minus beta decay. And what they have done, what in this experiment, what they have done is that they made the temperature very low level, that is at very low temperature, which means that in the normal temperature, if you consider normal temperature for cobalt 60, for cobalt 60 at normal temperature, this is not that much visible. At normal temperature, we have this cobalt 60, which will align, their spin can be oriented in any direction, random direction. So in this case, for cobalt nuclei, they will have spin oriented in random direction. I will say this random direction. So in normal temperature, cobalt 60 nuclei will have spin which is oriented in random direction. So when we make, so but they made, I think this is, they made the experiment, okay, experiment in a very low temperature, okay, in presence of magnetic field, also in presence of magnetic field. So what they have done, in normal temperature, if you consider the cobalt 60 will be having spin directed in random order, but when you lower the temperature and it is very small value, which is very cold, then the spin can align in some direction. With the application of magnetic field, you can make that spin aligned in a particular direction, that is in the direction of magnetic field. So that's what they have done. So along with the magnetic field and at low temperature, you can make the cobalt nucleus with 60, which is having a spin which is directed in a direction in such a way that that is the direction of the magnetic field. If you apply the magnetic field, so this is the magnetic field direction. So if you apply that magnetic field, then you can have the all these cobalt nucleus, their spin will be aligned in this direction, in the magnetic field direction. Okay, so this is at low temperature. So this will be the spin direction. So the direction will be like this, and so this is the direction. So these cobalt nucleus are now, it is at rest. They are not moving, but their spin are aligned in the direction of magnetic field. Okay. So this direction that I have shown here. Okay, these are the spin direction of these cobalt nucleus. Okay, these are the spin directions that I have shown here. These are the spin direction of these cobalt nucleus. So with the presence of magnetic field, they align in the presence of in the direction of magnetic field. Okay. So the nuclear spin of the cobalt is aligned in the direction of magnetic field, and as both the electron and neutrino, that is antineutrino in this case, electron and antineutrino has the spin. Similarly, both electron and antineutrino also has the spin. So both of them, since cobalt is at rest, this spin has to be in the field direction when there is a magnetic field, and the motion will be different. So if you are considering electron which is coming out of this cobalt nucleus, which will move in one direction, and the neutrino will be moving in the other direction. Similarly, if you consider the spin of this electron and neutrino, they also have to follow the same direction of the magnetic field, because under the magnetic field the spin orient in that particular direction. Okay. So in this scenario, for example, in the case of first scenario, we can see that this spin of all the cobalt, this is cobalt, and this is electron, and this is the neutrino, that is electron antineutrino. So when you consider this neutrino, antineutrino, cobalt, and electron, all of their spin aligned in one direction. Okay, all of their spins are aligned in one direction. I can show it in a different color. So this is this bigger arrow, which is the spin of this cobalt and neutrino. Similarly for electrons, this green color I'm now showing. So this is the spin, this block arrow or bigger arrow. But when we consider the case of, so this is the spin direction, and when you consider the case of motion or the momentum direction, that we can consider like this, and in this case it will be like this, that I already presented. So in the first scenario, we have the momentum direction or the motion, which is actually this should start from the end of this. Okay, so it is not. It's not. Okay, so this is the motion direction or the momentum direction. Momentum direction. Okay, that is the linear momentum. So which means that the neutrino is moving this direction, and the electron is moving in this direction, and you have your cobalt nucleus here, and you will be having daughter nucleus also after decay in this position. After that, cobalt will transfer into that daughter nuclei, and the antineutrino, which will be moving in this direction, electron will be moving in this direction. So this is represented by the momentum direction. Okay, so that is this red color arrow. So now that is first scenario. Now if you take the second scenario, okay, if you take the second scenario, then the electron can move in this direction. That is, the cobalt is at the center, and the electron can move in this direction, and the cobalt, which can, sorry, the new antineutron can move in this direction. Okay, that is also possible. It is not necessary that electron should move one side or one, but either of these two scenarios are possible. That the after beta decay, the neutrino can move in this direction, and the electron can move in the opposite direction, or the electron can move in this direction, and the neutrino can move in the opposite direction. Okay, so that is the second scenario. But remember that their spin align in the same direction because of the magnetic field. Spin will not change. Spin will be always in the direction of magnetic field, and we have applied the magnetic field in this direction. So their spin always try in that direction. So spin will not change. That is the bigger arrow that is represented here. So this bigger one, which will not change that direction. That spin is same, but the direction of electron and neutrino which is coming out can change. Okay, so when you consider the second scenario, in this case, when you especially check this case, we have the motion of neutrino in this direction and the spin in the opposite direction, which make this as a left-handed system. This is a left-handed system. And remember what is coming out in the cobalt decay process. What is coming out is the neutrino, antineutrino. So this is an antineutrino which is coming out in this direction, as I said. Okay, but spin in the opposite direction, which make them left-handed. But anti-neutrino with left-handed configuration, that is never observed. So this kind of process is not going to happen. So when they did this experiment, they always observed that electron will come in one direction, neutrino comes in the other direction. There is no other ways. So scenario, only the scenario one took place. Second scenario never happened. Okay, only this scenario happened. So when you have that this cobalt decay, there is only this electron which is moving in this direction only. Okay, so the electron never go in this direction. Okay, similarly neutrino, antineutrino which is coming out, which is going only this direction, which never go in this direction, which means that it never go opposite to that of field direction, which means that antineutrino will never follow a left-handed system, or it will never be, antineutrino will never be as a left-handed particle. So this confirms that in beta decay we have a violation of parity. Okay, we have a violation of parity because of the neutrino, and we say that beta decay is violating the parity. So parity conservation does not hold in beta decay or any in general we can say in any weak interaction forces or weak interactions, the parity will not be conserved and the parity is violated. Okay, that is the parity violation in beta decay process. So as a conclusion, we can say that the parity conservation tells that both the process are equally likely possible. That if you consider these two scenario under parity conservation, we can say that both of them are possible. But in reality, when you do that experiment, when Wu and his group did this experiment, it is found that electrons are always ejected. We can measure that electron path, and they are always ejected in a particular direction. Okay, so particularly in one direction, and which is opposite to the nuclear spin, that is spin of these particles, and never in the direction opposite to that of spin. Okay, electrons always emitted in direction which is in which is opposite. Okay, okay, this will be in opposite direction. That you can get from you can make that conclusion from this figure. Okay, so this observation says that in case of beta decay there is a direct parity violation, parity conservation violations, or parity conservation does not hold in that in beta decay processes, or in general we can say in weak interactions parity is violated or parity conservation is violated. So that is about the parity violation in beta decay process and Wu experiment that we already discussed.